Alright, so now we have studied Lagrangian and the Lagrangian relaxation and the Lagrangian duality. Those are actually fundamental knowledges, and they will provide intuitions for the following KKT condition. This is the main tool, one of the main tools that we need to use for solving optimization problems, nonlinear constraint problems. Okay, so this is an optimality condition. That means for any nonlinear program with constraints or without constraints, any optimal solution must satisfy this optimality condition. Okay, this is a necessary condition. Or we may also show that if the problem is a convex program, then this is also sufficient. So let's read the statements regularly. First, given any regular nonlinear program, okay, in this format, maximizing something subject to inequality constraints. Suppose x is a local maximum, then I'm giving you a necessary condition. If x is a local max, then we may find a vector lambda. Okay, lambda, we have lambda 1 up to lambda m, and that's the number of constraints. We may find a vector lambda such that the following three things are satisfied. First, x bar satisfies all the constraints. Okay, now this is of course required. X bar must be feasible for it to be optimal. And then this lambda, as you may guess, they are actually those Lagrange multipliers. So this lambda must be non-negative, and there is a weird equality here. Okay, the gradient of f equals the sum of lambda times the gradient of g for each gi. Okay, we're going to explain this equality details in later, but just think about the following situation. Suppose this is an unconstrained problem. Unconstrained problem means there are no constraints. Okay, so of course there is no right hand side, and that just means the gradient must be 0, or the first order derivatives must be 0. Okay, so you can see that this can be reduced to unconstrained problems. Or for constraint problems, again, we have this, and that's for constraints. The last one is lambda times the slake of each constraint must be 0. This is something very very similar to what we had for linear programs, right? For linear programs, we have the so-called complementary slackness condition. A pair of something times together gives you 0. Okay, so we can see roughly these three statements at least can be understood now. Okay, we're not going to prove the KKT condition, but at least you know what they are talking about and what's the thing to be verified. All the nonlinear programs in this course, and most of them in the world, are regular. Because of that, we're not going to give you a precise definition for regularity. Okay, in general, there are some ways to show or to prove a nonlinear program is regular or not, but most of them are regular, so let's forget it. And also, the condition is necessary for all the nonlinear programs, but it will also be sufficient for convex programs. Okay, so mathematically we have this. Let's try to interpret the condition. There must be some physical meanings of this condition, so let's try to do it. These are conditions for a local maximum, and let's explain them one by one. The first one, as we mentioned, we can say is primal feasibility. The original problem is some kind of primal problem, right? X bar must satisfy all the primal constraints for it to be primal optimal. So there's nothing wrong for this condition. And then we also need dual feasibility. Lambda is dual variables, right? So we know first lambda must be non-negative according to our knowledge about Lagrangian multipliers and the Lagrangian duality. So this is fine. And then we have this equality. Let's see it more carefully. We can see the equality is exactly the first order condition for the Lagrangian. Okay, the Lagrangian is this guy, right? The objective function plus sum of lambda I times gi minus bi minus gix. So this is exactly the Lagrangian. What the dual feasibility is saying is that I give you a problem, do the Lagrangian, and then an optimal solution must satisfy the first order condition for the Lagrangian. The Lagrangian or the Lagrangian relaxation is some kind of relaxation of the original problem. If a solution can be optimal to the original problem, it must also be optimal for the relaxed problem. Okay? And then that's why we have this condition intuitively. Again, I'm not proving anything, I'm just giving you an intuition. The intuition for this equality is that our optimal solution for the primal problem must also satisfy the first order condition for the relaxed program, for the relaxed Lagrangian. Okay, so if we do a gradient for this, we get the gradient for this one. And then for this one, this is a constant. It has nothing to do with x, so it does not show up at the right hand side. And then for each g, we have a gradient. Oh, sorry. This should be lambda I times gradient gi. Okay. So this is our result. The last thing, as we mentioned, is just complementary slackness. Dual variables times a primal slack must be 0. The number of constraints you have is the number of dual variables you have. Pair by pair, one by one. Lambda I times slack I must be 0. So we know several things. If a constraint is non-binding, then the Lagrangian multiplier must be 0, right? Non-binding means positive slack, means the multiplier is 0. This actually tells us a lot of things. For example, if there is a point satisfying all the constraints strictly, then all the constraints are non-binding. Okay? If there is, let me draw it. Suppose these are your feasible. This is your feasible region. Suppose there is a point satisfying all the constraints strictly. So none of these three constraints are binding on the point. Then, in that case, lambda must all be 0. So, lambda must all be 0. Okay? So, cancel this guy. The right hand side becomes 0. For this interior point, if we want it to be a local max, the thing it needs to be satisfied is that the first order condition must be satisfied. Okay? The gradient must be 0, which fits our intuition. So that's an algebra view for KKT. Let's also do a geometric view about, in particular, this equality. Consider that we have a problem like this. We want to maximize x1 minus x2, so we want to move in this direction. Subject to x1, x2 must be within this circle and without this circle, outside of this circle. Okay, and this is actually x1 square plus x2 plus 2 square greater than or equal to 4. Okay, so that means outside this circle. So the feasible region is here. Okay, graphically we can see that the optimal solution is at square root of 3 and 1. So it's somewhere here. This is the optimal solution and it is unique. The way we find it is through graphs. Now let's explain. What's going to happen to these three gradients at an optimal solution like this. Okay, so our objective function is f. I have gi and g1 and g2 as my constraints. First, let's do algebra. Gradient of f is 1 and minus 1. Oh, I hope this can be done by yourself. This is a function. A gradient must be a vector. The first component is the first order derivative with respect to x1. And the second component is the first order derivative with respect to x2. For the gradient g1 and gradient g2, that's the same thing, okay? Partial derivatives, partial derivatives. These are functions. So at an optimal solution, okay, at square root of 3 and 1, we may plug in those numbers and get these vectors. So graphically, we can see this is gradient f, this is gradient g1, and this is gradient g2. Okay, these are just simple algebras. Now let's explain what's the meaning for the existence of a lambda non-negative such that the equality is satisfied. If lambda are non-negative and we want to somehow combine gradient g1 and gradient g2 to make gradient f, okay? This is a vector, another vector, and we are asking you to combine the two vectors into the third vector. Then we're asking whether it is possible to do it with non-negative components or non-negative coefficients. If this is possible, if such lambda exists, then that means the gradient f must be in between g1 and g2. The concept of in between, it can be visualized on a two-dimensional graph. For a three-dimensional graph, it's also can be imagined, but it's harder to draw. But anyway, here it's simple. We have g1, gradient g1, gradient g2. Okay, so together these two guys will open a region, and within this region, I need to have gradient f. So that means if gradient f is in this direction, suppose, then you cannot find two non-negative lambda to combine g1 and g2 into the gradient f. Okay, so that's what's happening to this equality. I am asking gradient f to be within gradient g1 and gradient g2. Why do we need that for an optimal solution? Gradient f, roughly speaking, is the improving direction. If possible, I want to move along that direction. Okay, so I want to keep moving in this direction. How about gradient g1 and gradient g2? Gradient for less than or equal to constraints always point to infeasible directions. For example, for this circle, for this constraint, a gradient always points to the direction that is leaving the center. Okay, and for G2, because G2 is requiring points to be outside the circle, so G2 will always be pointing forward or pointing to the center. Okay, so in general, the gradients for constraints are pointing to those infeasible directions. So if gradient f, the improving direction, is within those infeasible directions, according to gradient g1 and gradient g2, then the point will be optimal, because you just have no improving direction, no improving feasible direction at this point. Okay, so you may feel, or you may guess, what's going to happen if gradient f is in this direction? Then there is some place, some tiny angles that we may move to, and that's going to make things better. Or what if gradient f is here? Gradient f is here. There's no non-negative lambda that can give you gradient f according to gradient g1 and gradient g2, then there is an improving feasible direction. Okay, so that's the intuition for this particular equality. If you can feel it, that's very good. If you cannot, at least you know how does it come from. It comes from the fact that we want a point to have no improving direction, no feasible improving direction. This is what contained in this equality. Okay, if you at least you need to know. Anyway, we need this equality. Then we may solve problems. Okay, so let's really solve this problem. Suppose I have this problem, and my first thing is always to get my Lagrangian. Objective function, constraint 1, constraint 2. Always use the larger part to minus the smaller part. And then I do the first order conditions with respect to x1 and x2, respectively, according to my Lagrangian. I can get this and this. They are just the outcome of first order derivatives. And then here is my KKT condition. A solution is a local max only if there exists lambda such that primal feasibility, dual feasibility, lambda must be non-negative, and I have these two equalities. Okay, and I have the Lagrangian, the first order condition for those Lagrangians is satisfied. And finally, I need complementary slackness. Okay, so primal feasibility, dual feasibility, and complementary slackness. And then let's look at this particular system. We have two original variables, x1 and x2, and two dual variables, lambda 1 and lambda 2. And we have four equalities, so it looks fine, right? 4 equalities, 4 variables. Somehow we may solve and get some candidate solutions, and that's how we move on. In general, if there are n variables and m constraints, always we will have n primal variables and m dual variables. But we will have n equalities from dual feasibility, the first order condition of the Lagrangian. We also have m equalities from complementary slackness. So we always have enough number of equalities to solve for variables. But unlike linear programming now, equalities may be nonlinear. So in general, there may be multiple solutions satisfying those equalities. Okay? And also those inequalities will then be used to eliminate some of these solutions. Anyway, a solution must satisfy all those equalities, inequalities, and so on. So sometimes it's also possible that no point satisfies the KKT condition. In that case, there is, of course, no local max. Okay, that's possible. Finally, if we have all the local maxima, or in general, we may have many, right? In general, we may have many. Then we can compare them for a global maximum. But at least nonlinear equations are hard to solve. And in general, comparing all of them may take too much time. If we want to get all of them and then compare, that may be too much time. So if a problem is a convex program, then it's really helpful because local mean or local max will be global max, and the number of points satisfying the KKT condition can be under control. Okay, but for general nonlinear program, even through this method, we somehow just cannot efficiently solve them. So we're not going to give you problems and asking you to run the KKT condition to compare everything in this course. That's not very useful. In this course, I just want you to know, first, there is a condition for nonlinear program. And the second, what we will do is to use this condition to some business and economic problems that are meaningful to us. Okay? And we want to use the condition to analyze and solve those problems so that we may do better decision making and get some more ideas about those problems. So again, what we will do is to use KKT conditions to solve, in some sense, simple business and economics problems so that we may get insights and get knowledge about those problems. One application will be given in the next video, and more application will be given in the lecture. Thank you.